Welcome back to CogX 2021. I'm Christine Foster, CCO at the Alan Turing Institute. We're the UK's Institute for Data Science and Artificial Intelligence, based just around the corner of the British Library. I'm calling in remotely, emceeing the research stage for this day. And across this whole festival, we're going to be addressing the question, how do we get the next 10 years right? We have CEOs, entrepreneurs, academics, artists, activists, policymakers, all working to realize the biggest transformational opportunities of our time. And we're going to start our next session in a moment. Do feel free to submit questions throughout the session for Q&A at the end. And also, most of CogX is free, so do invite your network to join in. This session is about securing blockchains against current and future quantum threats. It gives me great pleasure to introduce Kathy White, Technical Specialist at BT.
Hello, CogX. It's really great to be here, unfortunately virtually, but to be talking as well about quantum technologies, which is something that I specialize in my research at BT as part of the optical research team, where we're really excited about how quantum technologies can be very practical today, and we can actually send them over our real world BT fiber networks and use them for a number of different cryptographic tasks. So I'm really excited today to be talking to Duncan Jones, who is head of cybersecurity at Cambridge Quantum Computing, CQC, a company that's been around for 7 years now, early exploiter of the opportunities in the quantum software sector. So with no further delay, I shall say over to Duncan, who's going to talk to us about making the blockchain quantum safe, or safe against quantum computers. Duncan.
Thank you, Kathy. Good afternoon, everyone, or good morning, depending on where you're dialing in from. I'm speaking to you from just outside Cambridge in the UK. So my name is Duncan Jones. I'm the head of quantum cybersecurity at Cambridge Quantum. As Kathy said, Cambridge Quantum has been in the game for a surprisingly long time, considering we're a quantum-based company. And we have teams that are looking at every area where quantum computing is expected to bring some advantage. So that's in things like quantum chemistry, quantum machine learning, natural language processing. We also do quantum compilation, quantum operating systems even, and we do cybersecurity, which is the team that I lead. So the format of this session, I'm going to give a brief presentation now, about 10 minutes or so, on a project that we recently conducted in this area. And then Kathy and I will have a little bit of a discussion about the topic, and then hopefully we'll get a few of your questions in at the end as well. So I'll just switch to my presentation here. So this project was, the focus of this project was to take a normal enterprise blockchain and consider, how do you make this secure, not just against the normal threats that we face today, but the threats that we will face in a quantum powered future. So this was a project with numerous participants. We were not the only folks involved in this. It was really driven by the Inter-American Development Bank. They were very early adopters of blockchain technology. So they really understood the promise that this could bring. And in fact, they formed a consortium called LACchain, which was all about promoting and developing the use of blockchain technology in Latin America and Caribbean. That's where the name comes from. And so the challenge here was to take an enterprise blockchain. So we are not in cryptocurrency land here. Although the technologies are very, very similar, and the word Ethereum appears in both of these topic areas, we're in the world of private enterprise blockchains. So this means we have 10, 15, 20 participants in a blockchain, and the goal is to use the blockchain to establish a history of transactions, whether that's to move financial value around, whether it's to track a supply chain. There's lots of different reasons why people might use a blockchain. Now, the one caveat we had in this project is we needed to defend against the threats without modifying the blockchain itself, which added some complications, but as you'll see, we did okay in the end. So let's first talk about what is this problem I'm referring to here. So quantum computers are going to be able to solve some problems very, very well. And this is why we're so excited about them when it comes to things like material discovery or drug discovery, or machine learning even. This is because quantum computers, they just work in a completely different way to classical computers. And that means they can solve problems that are impossible to solve on classical computers. Now, the problem for cybersecurity is we tend to rely on mathematical problems that are very difficult to solve. So when you do some online banking or when you participate in a blockchain, under the covers, what you're doing is safe and secure because we think certain maths problems can't be solved. It's probably the easiest way to summarize it. Now, the problem is quantum computers can solve those types of maths problems very effectively. Not today, mind, but maybe in, let's say, 5 to 10 years, we could be in a position where quantum computers are powerful enough to solve all of these problems. And that essentially breaks cybersecurity as we know it today, and particularly blockchain, which relies very heavily on cryptography. So there's two real problems that we're going to face here. So the first is, as I said, the algorithms themselves. So the mathematical problems that we rely upon are going to be solvable. So the algorithms are going to be broken. That's problem number one. The second problem actually relates to the keys themselves. So when you do some kind of cryptography, you typically use a cryptographic key, and that is simply a chunk of random data. So if you imagine just lots of zeros and ones in an unpredictable pattern, that is a cryptographic key. And the security of that key is entirely dependent on, can anyone guess what that pattern looks like? And the idea is that nobody else can guess the pattern. And that allows you to use the key very much like your front door key. Nobody else can get into your house. Now, the problem is quantum computers are going to be very good at modeling and simulating complex systems. So this is why they are perfect for drug discovery and molecule. Well, I don't even know what you do with molecules, but they're very good at simulating how a complex system evolves over time. And this is a problem again for cybersecurity, because today when we generate keys, we tend to rely on complex looking systems that generate data that looks very random. So for example, you might use your laptop to generate a cryptographic key, and that will probably use some software algorithms that look very complicated and produce very random looking output. But it's not actually really random. Even if you use some dedicated hardware to generate your keys, and they often rely on even more complicated techniques, it's still not truly random. If you have a powerful quantum computer, we believe you will be able to model and simulate those systems. And actually, the outputs from those systems will be completely predictable if you have enough power. It's a little bit like predicting the weather. The more powerful our computers get, the better we get at predicting the weather, even though it's apparently a random phenomenon. So why are these two problems important? Well, it's because of, in particular in blockchains, it's because of what a blockchain is trying to achieve. A blockchain is trying to create this structured history of data, history of transactions that nobody can deny has happened. So it might be financial transactions or supply chain movements. And the problem is, if you have a quantum-powered attacker who can break the keys or the algorithms, then it allows them to introduce different versions of history that nobody else can dispute, because all of the maths will add up. Everything will look like this really happened. So you'll be able to create a completely different version of history that perhaps moves funds from your account to somebody else's account, or gets rid of a dodgy transaction that they wished never happened. This can all be possible once attackers have quantum computers. So, question then, what is the solution to this? Well, there are three parts to the solution. This is what we worked on in the project. So the first part is really the area where Cambridge Quantum delivered, I think, our greatest value, which is around solving the problem of having keys that are truly unpredictable. So we've been working on this problem for a number of years, resulting in a product called IronBridge. And ironically, we actually use quantum computers as part of this solution. So deep in the heart of quantum mechanics is true randomness. So if you think back to Schrodinger's cat, which is the example a lot of people can think of in terms of quantum mechanics, it's that kind of concept, the idea that when you open the box, you discover whether you've got a dead cat or an alive cat, or a 0 and a 1. That concept can be used to create completely unpredictable keys. And that's what we did as part of this project. We used our Iron Bridge product to generate perfect cryptographic keys. Now, although we can generate perfect AES keys and RSA keys, the goal here was to be fully quantum proof. So the keys that we generated for this project are known as post-quantum keys. So these are newer algorithms that rely on different mathematical problems that quantum computers can't solve, as far as we know. So we generated keys and we gave them to every node in the network. And then the next thing we did was we used those keys to create secure communication channels between the nodes in the blockchain. So in an enterprise blockchain, there's lots of messages that fly around between all the participants, and this is how they agree upon the contents of the blockchain. And obviously, it's important to make sure those are protected against any quantum-related threats. Now, because we couldn't change the blockchain itself, what we did was we created these secure channels that connect the nodes to each other using the perfect keys that were generated earlier. So that was step 2 of the solution. And the third and final step was to create quantum-proof transactions. And this ensures that in the future, a quantum-powered attacker cannot go back in the blockchain history and rewrite some transactions to say something that they wish it did say. And the way we did this is slightly complicated. I should draw attention, by the way, to the URL at the bottom of the screen here, which is where you can find the paper that underpins this work. But essentially what we did was we wrapped every transaction in a meta transaction. So it carried the original transaction as a payload. And then there was a post-quantum signature embedded in the meta transaction. And each node, before it replicates the data around the blockchain, it inspects the transaction, it inspects all the signatures, classical and post-quantum, and only if they are acceptable does it then add it to the chain. But the critical thing is the post-quantum signature makes it into the chain as well. And this means that it cannot later be modified by an attacker, even if they have a powerful quantum computer. So in summary, we believe that this work represents really one of the first practical examples of taking a blockchain and making it truly quantum proof. And we managed to do that without making any modifications to Ethereum. So the Ethereum virtual machine that was running on each of these nodes is the same standard one that you can pull down from Hyperledger or from anywhere else online. And what we've essentially done here is created a blueprint for introducing quantum safe security into blockchains. There's very little in this project that was specific to Ethereum. So the general concept could be picked up and applied to other private enterprise blockchains that are in use around the world. Now, before I come back to Kathy for a bit of a chat, I just thought this is CogX, so I need to get my crystal ball out and talk about the next few years. And what I wanted to just suggest was that we've talked about blockchain today, but really all of our cybersecurity solutions are going to be upended by this quantum threat. And if you're listening in today and you are in any sense a technology company, whether you consume it or you produce it or both, you need to be taking the threat of quantum very seriously. And that means getting people in your organization to explore this topic, to talk about it, to figure out how does it impact you. And the answers to the problems are, as we've said, to think about newer algorithms. And so to give you some context, in the next year or two, we will have some standardized algorithms that we can move towards. So the US government is really driving this process. We now have some finalists, and in the next few years, we'll know who the winners are. But it's critical that you start exploring now, because these algorithms are quite different to the ones that we have today, and you need to become familiar with that before it's too late. And finally, I predict that the method of key generation that we talked about today, where we use true quantum randomness to generate keys, I think that will become the de facto approach to key generation in the years ahead. And not just because it defends against a quantum threat, but because it fundamentally solves a problem that we've always had. How do we create true randomness for all sorts of use cases, including cryptography, where it's critical that keys are random, whether you're thinking about today's threats or tomorrow's. So that's what I had to present to you, and I imagine I'm going to go back to Kathy now, and she can grill me on it in excruciating detail.
Thanks very much, Duncan. That was really fascinating. So I think my first question would be, obviously customers need to be doing the threat assessment today, but do they actually need to take any action today, upgrading their systems? Because as far as we know, although quantum computers are developing, they're not really capable of crypto breaking today. No one's published any results which suggest that they can break RSA today. So should people be taking any action?
Very good question. Absolutely, I think. So when we talk to customers, a very typical question is, okay, when a quantum computer is going to break cryptography? And the truth is, nobody knows exactly when. Google's CEO went on the record last year suggesting it was perhaps 5 to 10 years away. Other people place it further out in the future. But you're right, the question is not when is it going to happen? The question should be, when do we need to act? And one of the things that I think people don't necessarily realize is that when encryption is broken by quantum computers, it will happen retrospectively. So, we're all talking today on a virtual platform, and there is cryptography powering this, and nobody can listen in today, and that's absolutely great. That's how it's supposed to be. But nothing stops people from recording this sort of information. And imagine it's far more interesting than our discussion. Maybe it's the financial transactions between two companies, or the intellectual property information between a big pharmaceutical company and its manufacturer. These encrypted connections can be monitored today because they're not very well protected, because people think, well, they're already encrypted. They can be monitored and recorded. And then when quantum computers arrive that are powerful enough, you can retrospectively decrypt the material that has been recorded. So now the question becomes, okay, let's say quantum computers become powerful enough in 10 years. Let's take the upper end of the prediction. Then you have to think, well, are we sending any information today that would be, embarrassing or costly or otherwise disastrous for it to become public knowledge in as little as 10 years' time? And in many cases, that's true. For most companies I speak to, that is true. And so that is one reason why early adoption and exploration is critical, because we already have a problem. Quantum attacks, to some extent, have already started. People are just patiently recording and waiting. And the other thing we have to consider is, when we talk about 5 to 10 years, we're talking about what is published information about progress in the field. Now, the good guys, if you want to sort of simplify things, publish this information. So we know what the Honeywells, the IBMs, the Googles are up to. But obviously you do have to question whether there are other people in the world who are working on these problems. They could be at a very different state of readiness. They could be further ahead even. So these are all reasons why doing your risk assessment now is important. And in many cases, adopting this stuff sooner rather than later, particularly for high value use cases, is really important.
I think as well, Duncan, you wrote in your paper about digital signatures and how, for example, if certificates were digitally signed today based on elliptic curve, DSA or RSA, then in future, if quantum computers are able to break RSA or DSA, then they might be able to, or they would be able to, generate fake certificates and backdate them, and therefore the integrity or the realness of those past certificates and bonds or whatever it is that's digitally signed would be unverifiable. So
That's absolutely right. And there's one area where that's particularly important is when you think about the Internet of Things, or connected devices. So we're seeing more and more devices coming online now in traditionally unconnected industries like heavy manufacturing, critical national infrastructure, and so forth. And when you bring devices online in that way, somewhere buried deep in the heart of the device is what we call a root of trust. So something that the device fundamentally trusts above all other things. That's how you build these solutions. You have this root of trust, and then everything comes off that. And this root of trust is how the device, when it boots up and comes to life, this is how it convinces itself the world is okay. So it switches on, and then it gets its root of trust, and it says, okay, is my operating system signed by my root of trust? Yes. Okay. Is my application signed by this key? Yes. And so forth. Now, the problem we have in IoT is that we're deploying devices into the field that need to last 15, 20, 30 years. That's well beyond even conservative estimates of when this cryptography will be broken. So that's another area where particularly these digital signatures and certificates are critical. And so anybody who's developing these sorts of solutions, particularly if you're building solutions where people die when they go wrong, you need to be thinking about adding in this security today. So you need to make sure your keys are being generated in an appropriate way. You need to be starting to adopt these algorithms sooner rather than later.
Thanks very much, Duncan. So just moving on to the iron bridge, the randomness, the quantum randomness, the quantum entropy that you're generating and delivering over the internet. So I've seen a number of QRNGs, quantum random number generators, on the market from a couple of vendors. Is there anything special about Iron Bridge? I mean, you said it worked on a quantum computer. Is there any reason? Have you done any metrics? Why should I trust Iron Bridge?
Good question. So one of the things we focused on at Cambridge Quantum was, and we looked at the reaction to the market to quantum random number generators, in particular what governments were saying about this technology. And as recently as last year, we had statements from the NCSC in the UK saying that while quantum technology has promise and it should be able to deliver the randomness that we're looking for, existing solutions are not basically hitting the bar. They're not able to prove their value because they cannot prove that they're actually generating randomness. And this comes back to my comments about the ability for quantum attackers to model complex systems. So existing QRNGs, as they're called, quantum random number generators, they are in that same category of complex systems that to the human eye, and even to some basic statistical tests, appear to produce randomness. But actually, they're very dependent on the way they're built. They're very influenced by environmental factors or imperfections in the way that they're constructed. So we took on board all of that advice, all of those comments, and we just took a completely different approach. And that's why we base our solution on quantum computers, because we can then run quantum circuits on those. We can play these special quantum games effectively with the quantum computer. So we challenge it, we get responses. It's very much a zero trust model, just to drop a buzzword in there. And what that does is it allows us to generate not just perfect randomness, but allows us to prove it's perfect. So the results you get from the machine allow you to prove that it is in fact perfectly random. And this is why I'm relatively bullish on the technology. I think we're going to see cryptography moving in this direction as its fundamental answer to the question, how do we generate random data?
I see. So it's self-certifying in a way.
Yes. So the way, without getting into too much details, the way the protocol works is it evaluates the quantum computer it's working with, and it can measure the noisiness of the quantum computer. So we're living in this world right now where quantum computers are not yet fully fault tolerant. And so we have this distinction between physical qubits versus logical qubits. And it's all about error correction and how much we can tackle these tough engineering questions of building these machines. And so part of our protocol involves basically interrogating the machine, and it tells us not only how much randomness that we can extract, but it also proves to us that we're working with a quantum device and that we can then trust this output and that it's actually purely random.
And will it be able to serve random numbers to all these potentially large number of blockchain nodes that might all need random number generation in order to seed the post-quantum process? Will it scale? I mean, will the Iron Bridge aspect scale?
Yes, no, absolutely. So, so I was just turning into a small pitch on Iron Bridge, which I didn't mean, but it's consumed as a cloud service. It can scale as far as it needs to. So, even if we are as wildly successful as I hope we are, we should be in a position where we can service the need that we see. Yes. You actually just to go deeper into that. Each bit of time we get on the quantum computer produces a certain amount of entropy, and then that's like a pure seed which creates further entropy as well. So there's a number of factors that kind of multiply up to create a lot of output, which is how we're expecting to service demand. Okay.
So it's some classical algorithms in there as well, potentially. So would this work? I mean, this solution that you created was very much a sort of enterprise solution, wasn't it? And it occurs to me that there must be a lot of customers who are in the position today where some of the things that they might be writing to their digital ledgers are potentially long-term sensitive. So could customers actually implement a solution like yours today on the blockchain? And is it something that has to be done over the top as you did, or could it be done more natively?
So yeah, I mean, what we've done today, I described it as a blueprint in the talk because the concept could be applied to a number of different types of blockchain or different use cases. But you're right that at the moment we're layering this over the top, and this is really the option that we have today in order to become quantum safe. The longer term answer, which I'm hoping we're moving towards, and to some extent I hope our work serves as some kind of thought leadership or an impetus in this direction, is for the blockchains themselves to start to migrate towards these new algorithms. So that pushes the security down into the blockchain itself, which makes it more convenient to implement. So in that setting, you still need to adjust your key generation approach, but this time you would just be then sending those keys to different nodes. You wouldn't need to then layer on those encryption tunnels or the extra signatures on the transactions. That would all then be handled by the blockchain itself. So that's where I hope we'll be in 5 years or so.
Will CQC be actively pushing blockchain developers to integrate this, into the native Ethereum, for example?
Yes, well, I mean, some of our partners in this project will be. IDB is quite interested in this space. They are planning to speak to the Ethereum development environment or crew and encourage them in this direction. So I can't claim that we're going to be the ones that spontaneously cause this to happen. Blockchain developers are smart people. They know this threat is coming, but I think it helps to build the pressure and show that there is demand from end customers of their platforms to have this security sooner rather than later.
Do you think that actually implementing this and making sure that there is a version of blockchain that is post-quantum safe could actually be a decision maker for someone like a bank when they're looking at technical solutions? Because I mean, a lot of banks, they're looking at blockchain, but they're not necessarily using it everywhere. They're not necessarily using distributed ledgers everywhere today. Could something like this be a deciding factor?
I imagine so. Yeah, I mean, blockchains have their fans and their enemies. A blockchain is not a solution to every problem, right? But where they are useful, they serve a very good purpose. And I imagine that when a bank is evaluating which technology to embrace, they will be considering, or I hope they're considering, the whole security landscape. And so if there were, for example, to be a blockchain technology that leads the way on quantum safety, then I assume they will attract more customers as a result of that.
And what about things like cryptocurrencies and proof of work blockchains, larger blockchains? Are they going to be affected, or will they just need to fork at some point before quantum computers arrive? And do they need to worry today or not?
So cryptocurrencies are slightly different. There are some there's some security that comes from operating at such scale. If you emerge with a different version of history versus the other 3 million people in your blockchain, it's going to be a little bit harder to pull that off. So cryptocurrency is a little bit different, but still they are based on the same algorithms that will be broken by quantum computers. So it is necessary at some point for those blockchains, and we're talking Bitcoin here or the public version of Ethereum, they will need to transition to newer algorithms. Now, I haven't seen the details yet of how they plan to do this, but I suspect it's a case of having a coordinated period of adoption across all of their endpoints. And then eventually new blocks will start being minted at the end of the chain that are signed purely by post-quantum algorithms. And that's when they can then look back and say their blockchain is now ready. So that definitely needs to happen. And the same comments around, the security of the keys and the predictability of the keys applies in a cryptocurrency as much as it applies in a private enterprise blockchain.
But perhaps at least all those people who've lost the keys to their Bitcoin wallets, if they get a quantum computer, they might finally be able to get those lost Bitcoins. You never know.
Yes, I guess so. But they're going to have to get there first, I guess, is the problem.
Yes, that's very interesting. So I'm wondering, does anyone in the audience have any questions?
I assume they're going to start appearing in our chat screen.
Yeah.
So while we're waiting, I'll maybe just talk a little bit more about this this competition that's happening in the US right now that I think everyone should be paying quite close attention to. So this is organized by the NIST, part of the US government, the National Institute of Standards and Technology. And about 5 years ago now, they put out a call to academics around the world saying, please submit your candidate algorithms to be evaluated and potentially chosen as the new algorithms that we'll all use globally. And NIST has done this plenty of times before. So AES, for example, which is a symmetric algorithm we all know quite well, that was selected through a similar process. And this process has been going on now for 5 years or so, and it had 69 candidate algorithms. Those were then whittled down, and we're now at our final 7. And so this is one of the reasons why it's fairly, a good idea to experiment right now, because we only have a handful of candidate algorithms. They're all relatively well understood now. So it's a good moment in time to explore this. And the next year or two, we will see those winners chosen. And I think that's suddenly when we'll have a huge rush of adoption. And so another reason to adopt early is because you can get a step ahead of your competitors who may be waiting around for this final decision to be made.
So we've got a question from the audience, from Vlad Ionescu, who's asked, did you explore wrapping already existing blockchain transactions in a meta transaction by adding a post-quantum signature? So I suppose, Vlad, that you're saying going back and adding some protection to previous transactions on the blockchain.
Yeah, it's a very good idea, Vlad. We didn't actually do that in this project, but it would be trivial to do so. We didn't constrain what the transactions were, so it would be relatively easy to make your transaction data a copy of a previous transaction and essentially seal it in time with a post-quantum signature. So absolutely, definitely possible. It's not something we explicitly did in this project.
But Duncan, if it's something further back in the chain, and then you've got a transaction that's got a post-quantum signature on it that's further down the chain, does that provide any, because it's sealed the chain up to that point, and then at that point it's post-quantum safe, does that in some way backwards inherit that post-quantum safeness to the previous transactions, even though they weren't post-quantum safe, or not?
That's a good point, actually. Yes, it probably will, because when the block is formed, it will contain the hash of all previous blocks. So it's a good question. I'm not exactly sure. I think it will seal it back in time, but certainly, for added confidence, or in case I'm mistaken there, it would certainly be possible to republish old transactions in this way.
I'm not seeing any more questions coming in, so final chance for any burning questions. But if not, I'm sure that Duncan will be very happy to talk to anyone who's. I mean, are you interested in helping other companies with their blockchain solutions today, making them post-quantum safe? Duncan, is that something that CQC actually wants to be doing more of?
Yeah, no, we would be very happy to speak to companies exploring the whole world of quantum safety. So if you head to cambridgequantum.com, you'll find us there. And I would look forward to speaking to people about this.
Well, we're already speaking to you, so yeah. Okay. All right. Well, that's been really fascinating, Duncan. Thanks very much for talking about quantum safe blockchain. I'm going to say back over to Christine. Thank you very much for having us. That was great.
Thank you, Kathy.
Thank you, Kathy. And thank you for taking the questions and leading us through a really in-depth discussion. I'd urge the audience to use this upcoming break to explore the virtual expo booths and the networking area. This is a fully hybrid festival, and so actually the next 2 sessions are happening in person at King's Cross. The next session's at 3 p.m., and it features Sir Andre Geim, Nobel laureate in physics, and I'll be just like you in the audience. I'll be following along online. Thank you so much.